Okay, welcome to another video. This video will be talking about sensitivity analysis in R. Essentially, how do you get R to give you as much information about the sensitivity analysis as possible without having to do it by hand? You'll notice that I've added an extra library here, the plugin library for lpsolve. You'll have to go ahead and install that package for this to work. But go ahead and follow along with the R Markdown file. We'll start off with our familiar example of Geppetto's workshop. Here is our optimization problem, our linear program here. And let's go ahead and run it and solve it. We'll begin by just using glpk as the solver that we've been using for all these examples. And we can get outputs of the solution. Optimal solution is to make 20 soldiers and 60 trains. We can get the objective value after solving and $180 of profit per week. And then we can get the status. And so actually I found if you look inside additional solver, $ROI, $status, that actually gives you the human readable message for the status. And so that explains a little bit more of that code 5 that I was talking about in the terminal conditions video. So it's solved to optimal, which is what we're hoping for. Not really worth doing sensitivity analysis if we run into an infeasible problem. Okay, so that is, yeah, that's just the basic stuff that we've already seen before. Now let's go ahead and get into sensitivity analysis. In ompr with the glpk library, which is the one that it's most naturally set up to work with, you can get a little bit of sensitivity information. So if we take our results and use the solution underscore row duals function sort of after a $ there, it will give us our duals. Okay, these row duals are what we've sort of been calling just the dual variables so far. These are the shadow prices, and they represent the increase in the objective for each unit increase in the right-hand side of the constraint. And so our right-hand sides represent the amount of finishing labor, carpentry labor, and demand for soldiers. And so these values here of 1, 1, and 0 represent that we're willing to pay $1 or every additional hour of finishing labor or carpentry labor, in this case, since they're both ones, will increase our profit by $1. Okay, whereas the demand for soldiers has a dual variable or shadow price of 0, meaning that it gets us no additional value by increasing the demand for soldiers, mostly because we're not currently demand limited. We're only making 20 soldiers, and the demand limit for soldiers was 40. Okay, we can also get the slack if we dig into it a little bit. Looking in the additional solver output. And actually, most of what we'll be doing in this video will be looking into that additional solver output, which is essentially ompr passing on exactly what ROI passes on to it, which is what it gets from glpk in this case. And if we change the underlying solver, it sort of passes back different additional solver output. So in this case, here's our right-hand sides of 180 and 40. And we can get this auxiliary primal, which essentially contains the constraint left-hand sides. And so if we do right-hand side minus left-hand side, that will essentially show us the slack in each constraint. There's maybe ways of computing this automatically instead of having, or computing this if it's not directly given to you. And so the other solver that we'll look at, lpsolve, won't give you the constraint left-hand sides. And so if you want to get the slack, you'll have to essentially extract the constraint matrix and multiply it by your solution vector. Okay. And I guess I didn't show an example of that, but I'll leave that to you to try out. The ompr package will also gives what it calls column duals. Go ahead and run that. These are essentially the reduced costs of the original variables. These are the final values in the tableau underneath each variable in the objective row. Okay, and so because both soldiers and trains are basic variables, they end up with 0 for the reduced cost. But in another scenario where we maybe had more products that we were considering, we might have one product that is non-basic, meaning that we're not making any of that product. And then that reduced cost would represent essentially the difference between the profit for that product and the value of the resources that that product takes up. And if it's positive, then that product takes up more resources than its profit. And so it sort of tells you how much you'd have to raise the profit while keeping everything else fixed in order to bring that variable into the basis. So a useful thing if you got some products that are non-basic. Yeah, let's see. Yeah, the row duals along with the column duals essentially give you the entire objective row of the final tableau. And so sort of putting that together, there are those two zeros, and here's the 1, 1, 0 of the dual variables. The objective value we can get from our result $ objective value, and we always have a 1 underneath the z in the objective row because it's the basic variable corresponding to the objective row. Yeah, and then here are the other items that you can find inside that additional solver output. It's mostly the things that we've already looked at. There's this tempting thing here that says there's a sensitivity report, NA. I looked around a long time in the documentation to see if there was some setting that I could set in order to get that sensitivity report to be generated. I couldn't find it for glpk. Maybe one of you will be enterprising and find it. I don't hold out much hope. I don't think it's actually implemented, though. I do know that ompr will pass things on to ROI. ROI can pass things on to glpk. I'm just not 100% confident what even setting to try to change. And so if you can figure it out, let me know. Okay. Now, that gave us a good amount of stuff. And I will say those are probably the two most useful pieces of information. The dual variables are probably the #1 most useful piece of information. The reduced costs, especially if you have non-basic variables, are useful information. But some other linear programming solvers give us more information. And so especially sort of the limits on right-hand sides or objective values that would keep the current basis feasible and optimal, okay? And that's why we're going to turn to using ompr with lpsolve. The beautiful thing is sort of ompr is a high-level interface that allows you to write your constraints in maybe an algebraic way that is nice and easily readable. It then passes the constraints and your objective down to ROI, which then passes on to the solver. The modular setup here allows us to swap out the solver for a different one if we want maybe different performance. I've done a little test, and at least for medium-sized problems, most of these packages have pretty similar implementations, and so run in a similar amount of time. If you get into a big problem, it might be worth sort of doing some robust testing and timing to see whether there's a efficiency gain from using one package over the other. But that's probably not worth worrying about until you get to really large problems. Okay, so lpsolve is one of the options. Another one is Symfony. There's a handful of other ones out there, including maybe some commercial ones such as Gurobi, I know is another one that you can put as the solver underneath the hood. Okay, so we're going to do the same thing. The only thing that really changes here is we change in the solve model command what solver we're using. So go ahead and run that. It gives us the same solution. Okay, you'll notice that its message will now tell us that it's using lpsolve to solve it, and it will tell us that it's optimal. lpsolve has a different set of codes than glpk. And so nice thing is that it does have this symbol here that will tell you essentially whatever lpsolve's code is for optimal. And hopefully it's a little bit more readable than just the number. Okay. So, unfortunately, I will say ompr expects its answers back in a certain format, and lpsolve doesn't give them back in the exact same format as glpk. And so the solver output's kind of broken for column duals and row duals. So if you try to run that, you'll get actually for column duals, you'll get something that's actually way too long. And actually, we can tell that it's not set up correctly. And then for row duals, you'll get a complaint about subscript out of bounds. Mostly, it's not the right size for what ompr is expecting as a library. Okay. But we still can get all the information. It's just hidden inside that additional solver output. Okay. The documentation is a little bit scant, but here's actually the best explanations that I've found of what lpsolve is giving back. And so if you take either of these two and put a question mark in front of them and paste them down into your console and hit enter, that will actually open the help file for these functions that are part of the lpsolve API, which is essentially the package that ROI is using underneath the hood to send the commands to lpsolve C library. The original lpsolve library is written in C. And so this is sort of the interface that's a kind of the level of ompr, ROI, lpsolve API, and then lpsolve C code is down beneath that. But that has descriptions of what the outputs are coming from that. Okay. So I'll explain it as we go what they are. So let's first look at the sensitivity for the right-hand side. If we run that, we'll get duals, duals from, and duals till. Okay, and you'll notice that each of these are length 5. And the length 5 in this case, kind of the explanation is that each of these will be length m plus n, where m is the number of constraints. And so the first, let's see, in this case, we have 3 constraints. So the first 3 entries of each of these correspond to your constraints. Okay, they are what we typically think of as our duals in a problem. Then plus n, the last 2 in this case, because we had 2 variables, are correspond to the decision variables. Okay, these are our column duals as we previously saw. And so we see the same row duals of 1, 1, and 0, and the same column duals of 0 and 0. They're just in a different order than maybe I would necessarily expect. Okay. The duals from and duals till give the lower and upper limits values on the dual variables. More of they give you the lower and upper bounds on the right-hand sides. Okay, and so the first 3 are giving you the lower and upper bounds on the right-hand sides of those functional constraints. The last 2 are essentially giving you the lower and upper bounds for the right-hand side of the non-negativity constraints. Okay, or if a variable has an upper bound, then therefore the upper bound constraint. Okay, in this case, we just had lower bound constraints. So let's kind of dig into that in this problem. Looking at it from the duals from and duals till, anytime you see a 1 plus e or 1e plus 30, that stands for 1 times 10 to the 30th power, which would be 1 with 30 zeros after it. That is essentially the upper limit for the largest number that the lpsolve library thinks about. Essentially, it's saying, as far as lpsolve is concerned, it's infinite. Okay. So looking at the first 2 entries here, we see 8e1, which is 8 times 10 to the first, or 8 times 10. Excuse me. 80 to 1.2e2, so 1.2 times 10 to the second, or times 100. And so we see that the first constraint, or the amount of finishing labor, the current basis is still feasible, provided the amount of finishing labor is between 80 and 120. And that corresponds to what we worked out when we did this problem, pencil and paper. For the carpentry hours, that's between 60 and 100. And the thing to remember about these is that we're assuming that we're only doing one change at a time. So you can't simultaneously change the finishing to 80 and the carpentry to 60 and expect that the current basis remains feasible. It's sort of if you fix the carpentry hours and change the finishing hours, or if you fix the finishing hours and change the carpentry hours. Okay. What you'll notice for the third value here, it goes from essentially negative infinity to infinity for the limits of the right-hand side of the demand for soldiers constraint. When we worked this out, we saw that there actually was a lower bound for the demand of soldiers of 20, in that we're currently making 20 soldiers, and if we have a less than 20 soldiers worth of demand, then then we can't make those 20 soldiers. But from what I can tell, lpsolve does is it gives infinite bounds if a constraint is not active. Okay, so in this case, there's slack in the demand for soldiers constraint, and so it essentially is ignoring that constraint, at least in as far as it's giving these bounds. So there is some bound on how much we can change the demand for soldiers. But as long as it's a small change, it should be fine. In essence, as long as we change it enough that our current solution is still feasible, we're fine. Yeah, so yeah, that's something to kind of be aware of. The last two are essentially negative infinity to positive infinity on those non-negativity constraints, mostly because we're making some soldiers and some trains, and so those non-negativity constraints are not active. They're not limiting, and so again, it gives us sort of infinite bounds on the right-hand side of those non-negativity constraints, which is kind of weird, but that's the way it does it. So anytime you see kind of negative infinity to infinity, doesn't mean that you can make it anything. It just means that whatever constraint is currently not active. Okay. lpsolve will also give us sensitivity information about the objective function. We run this, it'll give us objective from and an objective to. These are lower and upper bounds for the coefficients of the objective function. Right now, their current values are 3 and 2, but we can see that if the profit from soldiers is between 2 and 4, or if the profit from trains is between 1.5 and 3, our current basis will remain optimal. And in this case, the actual solution doesn't change as long as we're within these bounds. Remember that we're changing only one of those at a time. If we change multiple ones at a time, then we've got to use another trick or kind of consider that separately. But if we kind of consider only changing one at a time, we could change the profit from soldiers anywhere between 2 and 4, and the current basis will remain optimal, and we'll still make 20 soldiers and 60 trains. Okay, so that is for the Geppetto problem. Let's do another example where we can see it, and we'll return to the WIT window example. Kind of recall that they're making wood framed windows and aluminum framed windows with 300 and 150 as the respective profit per window. We're limited on labor on how many wood windows we can make, up to 6 a day, and aluminum we can make up to 4 per day. And then we also have a limited resource of glass of 48 square feet. And it takes 6 for wood framed windows and 8 for glass framed windows. We were able to accomplish this model in ompr with only one constraint by making use of the upper bounds in our variable definition. Okay, and most linear programming solvers do a kind of special trick when you provide an upper bound, is that they don't actually implement those upper bounds as a separate constraint, but do a trick where they sort of will swap back and forth between the original variable and the slack from that upper bound sort of as needed. And because we're never going to hit both the lower bound and upper bound at the same time, it kind of gets away with sort of maybe adding an extra variable, but not an extra constraint. And constraints tend to be what cost more in regards to solving a linear problem. Okay, so let's go ahead and run this. We'll get our optimal solution of 6 wood framed windows, 1.5 aluminum framed windows, assuming we can make part windows in a day, and that would be fine. Or maybe you pick up the work on it on the next day. And we get a optimal amount of profit of $2,025 per day. It's solved to optimal, so that's good to see. Now let's look at the sensitivity analysis. Looking at the right-hand side, we get duals of 1875, 187.50, and 0. Okay, what we want to interpret this as is this is the dual for the one constraint that we have. So this is the shadow price for the amount of glass that we have available. So we're willing to pay 1875 per additional square foot of glass that we could obtain. This is dual variable corresponds to the upper bound on wood framed windows. Currently, we're limited by that upper bound. We're making 6 wood framed windows, which is exactly the upper bound. We're willing to pay $187.50 if we can find a way to let Jacob make an extra window. Or on the flip side, if Jacob makes fewer windows in a day, we're sort of eating or we're losing $187.50 in profit. Okay. And then for the aluminum framed windows, there's 0 for the shadow price because we're not currently limited either the upper bound or the lower bound for aluminum framed windows. We're making 1.5 of them, which is between the upper and lower bound. Okay. If we look at the from until, the current basis will remain feasible if we have between 36 and 68 square feet of glass. We'll still make the same strategy of essentially making as many wood framed windows as possible, hitting the upper bound on that, and then essentially using up all of our glass so that we're kind of glass limited. And then we'll also have the current basis remain feasible if Jacob can make at least 2 2/3 windows up to 8 windows. My guess is that if he can make more than 8 windows, then we maybe stop making any aluminum framed windows. And if he can make less than 2.67 wood framed windows, then maybe we start making more aluminum windows instead. Or yeah. When we first met this problem, we did kind of ask some of these sensitivity questions of what would happen if Jacob cut back his hours so that he could only make 5 wood framed windows. And we sort of just resolved the problem, changing that upper bound down to 5. But with these duals, we know essentially what that answer is without having to rerun the problem. In that by reducing his number of windows that he's making down to 5, it's still within this range of between 2 2/3 and 8. So the current strategy or the current basis will remain optimal or feasible. And because the dual value placed off on that upper bound is 187.50, we're going to lose exactly 187.50 in profit. And so the daily profit will be reduced by that amount down to 1,837.5 or $1,837.5 per day. Okay. It's a little bit trickier to find out what is the exact solution at that with the reduced number of hours because as far as I can tell, none of the packages directly give you the B or B inverse matrices. I will say you can use extract constraints to get the full constraint matrix, which then you could essentially choose the basis columns from that. in order to form the B matrix, and then you could invert it. So you can get there. In this case, it's a small enough problem that we can kind of just think through it logically, and that if we keep the current basis, we're going to be limited by glass and by wood frame capacity. So he's going to make the full wood frame capacity, which if we reduce that to 5, he would mean making 5 wood frame windows. And then he will use up the remaining glass capacity by making aluminum windows. And so we can take that glass capacity constraint and turn it to an equality constraint. And then because we know the value of wood, we can then solve for the value of aluminum. And if you solve that out, it ends up being now 2 1/4 aluminum framed windows. And so we were able to increase the aluminum framed windows by 0.75 in this case. Okay. If we look at the sensitivity for the objective coefficients, we get an upper bound, or no, a lower bound for actually both of them. We do see an upper bound for aluminum framed windows. So the current basis will remain optimal, assuming only one of these changes happens at a time, as long as the wood framed profit is at least 112.50. Okay, and then the profit for aluminum frames is less than 400. So if we are able to increase our margins enough on the aluminum framed windows, we probably switch over to making as many aluminum framed windows as possible instead of wood framed windows. And so we'd have a switch of basis, which would represent a switch of strategy. The lower bound of 0 there is really, we shouldn't expect to ever make a product that has negative profit. And so if the aluminum framed windows started having negative profit, we would immediately stop making any aluminum framed windows. Okay. And we saw that in the previous time we met this example. We could lower the amount of profit for wood frame windows from 300 to 200. It would change the profit, but it wouldn't change the optimal product mix. But if we reduced it down to 100, then we had a change in the optimal product mix. Okay, so that's this example. Let's do one more quick example. Just that's a little bit different. It's going to be a minimization problem this time, looking at the capital budgeting flow model problem, where we need to cover capital expenditures of 2 million, 4 million, 8 million, and 5 million in 4 consecutive years. And we've got different interest rates for bonds sold in those years. And we want to minimize essentially the interest payment over the 20 years after the bonds are sold. So we can kind of make short-term 1-year deposits that yield some interest, not as much as the bonds are charging, but some interest. If we go ahead and run this, here's that extract constraints command that I mentioned. It can get you that constraint matrix if you wanted to actually find the B matrix, which would correspond to the basic columns. And then if you wanted to find the B inverse matrix, you'd have to then invert that. Okay, let's go ahead and solve it and look at the result. The optimal or the minimum yearly interest payment ends up being just over 1.1 million per year. And we get to that by selling just enough bonds in year 1 to cover year 1's bond or year 1's capital requirement. And then we sell all of the rest of the bonds needed for the project in year 2 to cover year 2, year 3, and year 4, accounting for the fact that we're going to get a little bit of carryover interest on the deposits between the years. Our flow variables essentially record how much flows between year 1 to year 2, year 2 to 3, 3 to 4. Notice I kind of made an artificial flow variable in year 4 that we expect that to always be 0. Mostly because it would mean that we're selling too many bonds in order to get extra money in our bank at the end of the 4th year. Okay, so let's do some sensitivity analysis on this. I will say if you stick the output of these sensitivity things into a data frame, they become a little bit more readable. And so doing that, it kind of turns it into column format and we can kind of look at them. And so the most interesting things here are really just the first 4 columns that deal with the actual constraints. The other ones that deal with the variables are maybe a lot less interesting or useful in this scenario. So the duals for the first four rows of 7%, 6%, 5.7%, and 5.4% are essentially the effective interest rates on bonds in those years. So the first 2 years, they're exactly the bond interest rates that we'd be charged. In years 3 and 4, those are the effective rates accounting for the fact that we get interest on the deposit carrying those forward. And they're actually the effective rate based off of selling those bonds in year 2. Okay, so we get we lock in at year 2's bond rate, and then we actually gain some extra by carrying it over between the years. Yeah, that's the way we can sort of interpret the shadow prices in this scenario, is the sort of cost in the interest payments over the 20 years after the project is done, for each additional $1 million spent on the project. And so essentially that is just the effective interest rates. Okay. The duals from and duals till in that case tell us essentially when will our strategy switch, or what sort of bond requirements would cause our strategies to switch. And in this case, as long as the first year's capital amount required is some positive number, we're going to sell just enough in that first year to cover it, mostly because the interest rate in year 1 is higher than year 2. Okay. Similarly for year 2, as long as the capital requirement is actually some positive number, because the lower bound is negative, we're not really going to worry about negative values. We're still going to follow the same strategy, and actually same thing for year 3 and year 4. And so as long as what we'll see is that our problem doesn't really depend on, or our strategy doesn't depend on the capital requirements at all in this case. No matter what those capital requirements are, as long as they're positive numbers, we're going to follow the strategy of sell just enough in year 1 to cover year 1's capital requirements, and then sell all the rest in year 2 to cover the rest of the project. Okay, and that's based solely on the interest rates. Okay, so that's kind of an interesting result that we can see from the kind of limits on the right-hand side. Okay, we get maybe a little bit more interesting things happening with the sensitivity of the objective function. You go ahead and run that. We see really the first 4 are for the amount of bonds sold variables. The next 4 are for the flow variables. The ones corresponding to flow variables aren't very interesting, but we'll see that the current solution will stay optimal provided the first year bond interest rate is at least 6.36%. If it drops below that, we actually might sell all our bonds in year 1. The current solution will also stay optimal provided the second year interest rate is between 0 and 6.6%. If it were to go above 6.6%, then we'd probably choose to sell our bonds in a different year. In the third year, as long as the interest rate is over 5.7%, then we're going to sell, we're going to keep our same strategy. But if it were to drop below, we'd probably sell our bonds in year 3 instead of year 2. And similarly for year 4. So these are sort of the thresholds in evaluating. You might not be 100% confident. And my guess is that if these are forecasts of bond rates, there's a pretty decent error bar on those forecasts for the bond rates in the coming years. But as long as you can be confident that in year 3 and year 4, it's going to be something over this, then you'd go with this bond strategy. Okay. And maybe you'd actually, in practice, what you'd do is you'd sort of solve this in year 0 with a plan, and then update it and resolve it after the first year with a better forecast of the bond rates, where you know some of them for sure. So, for example, you probably know the bond rate for the first year definitely, because your bank probably tells you that's what it is. But you're probably using some forecasts for the later years. Okay. And this sensitivity analysis, instead of needing to be, well, there's huge error bars on these, it comes down to a yes or no question. Is the bond interest rate in year 4 going to be over 5.44%? If so, I'm going to use the same strategy that I already have. Okay. So that's it for this video of examples of using sensitivity analysis in R.